Hi everyone. If anyone came to my office yesterday during office hours, I want to apologize for not being there. I was still in bed recovering. So today is yet another lecture on sorting. And I'm going to cover 3 different topics today. So it's a vignette day. The first topic is called selection, which is kind of an offshoot of sorting, and we'll see why. It's virtually the same algorithm. Suppose you want to find the kth smallest key in a list. A list that is not sorted. So finding the smallest key, you have to walk through the whole list, for instance, and figure out which key is smallest. But what if you want the 20th smallest key? Are you going to keep a list of the 20th smallest items you've encountered so far? There's a better way. So another way of saying this is I want to find the item at index j if the list is sorted, or if the list were sorted, where j is equal to k minus 1. So here I'm assuming that we're indexing arrays from 0. Therefore, j equals k minus 1. So one obvious way to do this is first sort the list and then look up index j. So that's easy, but sorting, well, typically takes n log n time. And so you might ask, can we do this faster if we don't need to sort the whole list and all we need to do is find the kth smallest key? And the answer is we can. One example of this is finding the median. People very often have a data set and want to find the median number in that data set. So the median of a set of n keys means the item whose index is n minus 1 over 2 in the sorted list. Or at least that's its index if n is odd. If n is even, of course, there are 2 median keys, and you can usually pick either one for most applications. And so round up or round down when you divide by 2. So let's find that. The algorithm we're going to use for doing that is called quick select. And hopefully it will come as no surprise that quick select is a lot like quick sort. So here's an algorithm that finds the item at index j, or the item that would be at index j if the list were sorted, but it's not. In other words, the j plus 1th smallest key. It works like this. It starts off exactly the same as quicksort, really. So we start with an unsorted list, I of n input items. We choose a pivot, as usual, using the same strategies we did for quicksort. Then we partition I, the same way we did before. And we're going to do this so that IV will contain the pivot V. And as before, just like with quicksort, items with the same key as the pivot can go into any of the 3 lists. And in practice, that means that when you're doing list-based quicksort, you'll want to put them into IV. And if you're doing array-based quicksort, we use exactly the same partition step we did for quicksort, so they go into I1 and I2. All right, so where things are different is at the end when it's time to do quicksort recursively. In quicksort, we have these two arrays, I1 and I2, and we recursively sort them. But for selection, we only need to look into one of them. And since we know how many items there are in I1 and how many items there are in I2, we know which array we have to look into to find the j plus 1th smallest key. And here's how we do it. If the index j we're looking for is less than the size of the list I1, then we look in the list I1. So we recursively run quick select to find the item with index j in list I1 and then return it. In this case, we do not have to go look in I2 or sort I2 at all. Second possibility is that the index j is somewhere in the space of the pivot or the keys that are equal to the pivot. And if that's the case, we just return the pivot. And the final case is that it's not in the keys that are less than the pivot. It's not one of the keys that are in IV, the pivot, or maybe other keys equal to the pivot. So it must be one of the keys that's in I2. Now we have to be careful about indexing. We are looking in I2. So within I2, the key we're looking for will have index j minus the length of I1 minus the length of IV. And so that's what we look for. And so that's how you do selection. Any questions on that so far? So the big advantage of quick select over quick sort is that we only have to do one recursive call instead of two. And we only do one recursive call at every level of the recursion tree instead of two. So over a lot of levels of the recursion tree, that's really adding up to a big improvement. And so quick select runs in theta n average time, expected time, for those of you who know a little probability, if we select pivots randomly. I'm not going to prove that today, but I'm going to analyze quick select and quick sort later on this semester in a lecture on randomized algorithms. One other thing I want to point out is that if you're using the array-based quicksort, you can pretty much take the code that I gave you for array-based quicksort and adopt it slightly. So in that array-based code from lecture 31, you might recall that there's a variable called I. And, well, basically, you can substitute that variable I here. The length of I1, in that case, is the variable I from that pseudocode I gave you. And in the array-based quicksort, since it's hard to maintain 3 separate lists while we're partitioning an array in place. IV is always equal to just 1, because we put all the other keys equal to the pivot into lists I1 and I2. Any questions about that? Okay, well, let's go on to our next topic then. One of the harder topics of computer science is proving lower bounds on how hard it is to solve a problem. I'll show you one example of how to do that that's pretty critical for computer science. So there's a big difference between proving lower bounds on problems and proving upper bounds on algorithms. To prove an upper bound on an algorithm, you devise a specific algorithm, and you show it that it works, and then you prove that that particular algorithm runs in a certain running time. But lower bounds are generally different. For a lower bound, you have to prove that for any algorithm that anyone could ever think of to solve a given problem, it can't run faster than a certain speed. And that's much harder to do because you aren't looking at a specific algorithm. You have to prove that nobody will ever dream up an algorithm ingenious enough to solve a problem faster than a certain speed. Well, we can actually do that sort of for sorting as long as we place a restriction on how people are allowed to sort, which is they have to do a comparison-based sort, which means that every decision you make on how to reorder the data is done with an if statement. Now, all of the sorting algorithms we've looked at so far this semester are comparison-based sorts. Most of the sorting algorithms you would think of are comparison-based sorts. So this applies to, most of the sorting algorithms you would think of. And what we can do is we can prove that these kinds of sorting algorithms cannot run faster than n log n time. Question? Absolutely. That'll be the third vignette today, and all of next lecture will be non-comparison-based sorts. Yeah. Mm-hmm. 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 Huh. That's very strange. Okay. I can't think off the top of my head what would have caused that. That's interesting. I guess maybe I should look at the code later on. No ideas right now, though. As a prelude to this, suppose that you have a scrambled array of n numbers and each number from 1 to n occurs exactly once in this array. So let me ask, if you have n scrambled numbers, the numbers 1 to n, each occurring once in scrambled order, how many different orders can they be in? The answer to that question is n factorial. For those of you who haven't seen n factorial before, what that is it's the number you get when you multiply 1 times 2 times 3 times 4, and so on all the way up to n. Now, why can there be that many different orders? Well, here's why. Let's suppose that I scramble my array as follows. I have all the numbers from 1 to n. I randomly choose one of them, and I'm going to take that random choice and put it in the very first spot in my array. Well, how many possible ways are there I could choose that number? Well, there's n different numbers, so I have n different ways that I can choose the first item in my array. Once I've done that, how many different ways are there I can choose the second number in my array? Well, I've chosen the first number and it's stuck there. I've got n minus 1 numbers left to choose from to be the second item in my array. So I take one of those n minus 1 choices, and that means there are n times n minus 1 different ways I could choose the first 2 items in the array. There's n minus 2 items left, so that's n minus 2 choices I could make for the third item. So there's this many ways I could choose the first 3 items. And if you continue this logic all the way down the array, you get this many ways to order n numbers. Now, each different order of the numbers 1 to n is called a permutation of those numbers. And so what I'm saying is that there are n factorial possible permutations. All right, so before we get back to discussing how this relates to comparison-based sorts, I want to figure out how big the logarithm of n factorial is. And so let me make a few observations. The first one is n factorial, since it's equal to 1 times 2 times all the numbers up to n, well, I can find an upper bound for that by replacing all of those numbers by n. So obviously, that is less than n multiplied by itself n times. Which is equal to n to the nth power. So that gives me an upper bound for n factorial. It can't be bigger than n to the nth power. Let's do a lower bound now. Lower bound is just a little bit trickier. The way I'm going to get a lower bound is I'm going to just throw away the first half of the factors. So I have n over 2 factors left. And that is greater than or equal to a whole bunch of n over 2's multiplied together n over 2 times. And so that's n over 2 to the power of n over 2. So that gives us a lower bound. N factorial has to be a number between this number and this number. And so now let's look at the logarithms of those numbers. Well, the logarithm of n over 2 to the power of n over 2, well, there's a standard identity for logarithms that says you can take the exponent and put it in front of the log as a multiplier. And so that is in big theta of n log n. And if we take the logarithm of the big one, the upper bound, n to the n, well, that's just equal to n log n. And so if n factorial is between this number and this number, then if we take the logarithm of n factorial, then that is in theta of n log n. Yeah. This one here? Okay. Well, I have all the numbers from 1 to n here. I throw away the first half of them. So now I'm starting at n over 2. And so I have to put a greater than sign here. N factorial is greater than what I have left over after throwing away all the first half of the terms. Now, the number of terms I have left over is still n over 2. And so I do another approximation where I say, well, all of those terms are greater than or equal to n over 2. So I'm going to just take each of these terms and replace it with n over 2. So now I'm multiplying n over 2 by itself, n over 2 times. Okay, so now I'm going to come back and use this to talk about sorting algorithms. All right, coming back to comparison-based sorts. A comparison-based sort is a sort in which all decisions are based on comparing keys. Which is typically done with if statements. So all of the actions that are taken by the sorting algorithm are based on the results of a series of true-false questions. And all of the algorithms that we've studied so far, as I've said, are comparison-based. This is how they work. They do a bunch of if statements, and based on comparing different items, they decide which swaps they're going to make and how they're going to reorganize the data. All right. So let's do a little thought experiment. Suppose that we run a comparison-based sorting algorithm twice on two different permutations of the numbers 1 through n. And suppose that as both algorithms run, they get the exact same answer to every if statement. If one algorithm gets a true, the other one gets a true. If one algorithm gets a false, the other algorithm gets a false. Then both algorithms are going to perform exactly the same sequence of statements in the same order, and therefore they're going to rearrange the data in exactly the same way. But I said that they started off with two different permutations. So this must be a buggy sorting algorithm because you can't sort two different permutations in exactly the same sequence of operations. You have to do something different to sort the one sequence than what you do to sort the other sequence. In other words, if you have a correct sorting algorithm, then it has to have a different sequence of true and false answers as you run through the code for each different permutation that you could imagine sorting. So takes a little thought to believe this, so I'm going to write it down. A correct sorting algorithm, again, must generate a different sequence of true-false answers for each different permutation of the numbers 1 to n. Because it takes a different sequence of computations to sort each of those permutations. So because there are n factorial different permutations we could sort, we need to have at least n factorial different sequences of true and false answers. So if an algorithm asks at most d true or false questions, how many different ways could it treat the data that it's sorting? Well, the answer is 2 to the power of d, because if you have d different questions, and each one can be true or false, that gives you 2 to the d different possible sequences of true and false answers you could get. So our algorithm generates at most 2 to the d different sequences of true-false answers. Now, again, if it correctly sorts every permutation of 1 to n, then the number of sequences of true-false answers has to be at least as big as the number of different permutations. So n factorial has to be less than or equal to 2 to the d, or our sorting-based comparison algorithm, or comparison-based sorting algorithm, doesn't work. Now let's take the logarithm of both sides. The log base 2 of n factorial is less than or equal to d, is what this says. And we know that this thing is in big theta of n log n, so d has to be at least in big theta of n log n, or bigger. In other words, d is in big omega of n log n. Any questions about that? Yeah. Well, one thing is that since n factorial generally isn't a power of 2, it can't be exactly equal. But so if an algorithm asks d different yes-no questions, then it can sort the data in up to 2 to the d different ways, but it could be less than that. Like not every single possible sequence of true-false answers will be used or is even possible. So generally, 2 to the d is going to be bigger than n factorial. But as long as it's bigger, we can have a sorting algorithm that works. So the final thing oh yeah, question. Uh-huh. I just made an arbitrary decision because I wanted to get an asymptotic lower bound, and that decision was good enough to get theta n log n. If you picked 1/3 of the items or 2/3 of the item, you'd still get theta n log n that way too. So it doesn't really matter. It's just I'm sloppily throwing things away, and I still get a tight enough answer, so I'm happy. So the last observation we have to make is just this. The amount of time it takes to ask d questions is d time. You cannot ask d questions in less than d time. That's kind of obvious. Every if statement takes a constant amount of time. So if you believe that, the algorithm spends theta d time asking d questions. And since d has to be in at least as big as n log n, that means, in conclusion, every comparison-based sorting algorithm or at least every correct comparison-based sorting algorithm that actually works, takes omega n log n worst case time. Notice that that's an omega, so n. Since this is an omega, of course, there can be algorithms that run slower, like selection sort. But if they want an algorithm that runs faster, it can't be comparison-based. Questions about that? So if you want a faster algorithm, you need to forget about two-way decisions. You have to make q-way decisions for large values, for arbitrarily large values of q. And you can't do that with an if statement. So how can you do it? We're going to start off with a special purpose sorting algorithm called bucket sort. And eventually we're going to move up to a more serious, more general purpose sort next class. But for now, bucket sort's a little bit limited. It works well when the keys are distributed in a small range. Like from 0 to q minus 1. In other words, when q is in big O of n. So it's a bit limited. If you have to have keys that fit in a very small range. If you're only sorting 100 keys, then this will work if those keys are in the range from 0 to 100 or even 0 to 200, but you don't want to let them get too big. Later, we'll see how to get around that difficulty. But for now, let's start simple. Here's how our algorithm works. We're going to have an array of QQs. These could be just singly linked lists with tail references, which are basically the same things, but we're just going to use the Q operations exclusively. And these are numbered from 0 to n minus 1, or sorry, to q minus 1. And these queues are called buckets, just like in hash tables. Now, the algorithm works like this. We walk through the list of input items, and we enqueue each item in the appropriate queue. So key number I goes into queue number I. So now I'll draw this algorithm so you can see how simple it is. Suppose our input looks like this. So what I've done is here I've got a bunch of keys, which are the numbers. And next to each key, I have an associated item, which are the elements associated with the keys. And those will help us see how things get, what order things get sorted in. Now the keys here range from 0 to 7. So my queue fronts are going to be numbered from 0 to 7. So let's go through and sort these. Start with the first input item. Its key is 6, so I take it and I put it into the 6 bucket. Next item is 7, so I take it and put it into the 7 bucket. Next item is a 3. It goes in the 3 bucket. Next bucket is 0. Our next item is 0. Goes into the 0 bucket. We have another 3. So that gets concatenated onto the end of this queue, which is why we have tail pointers and why we use queues. Next comes the 1. Then the 5. Then a 0. Then another 3. And then a 7. All right. So now I've gone through the list and I've thrown everything into the buckets. And the last step is to concatenate the queues together in order. In order by bucket. So our final list is going to look like this. Our output list is going to start here, and then we're going to link the queues together like this. And that's the end of our output. So our output comes in the form of a list. And by the way, this data structure is exactly like a hash table. In fact, it is a hash table where the hash code just maps every key I to bucket I. Any questions about this? So the running time for this is theta q plus n. And that is in the best case and the worst case. It always takes q plus n time. It takes theta q time to initialize the buckets and to concatenate them together. And it takes theta n time to put the items in their buckets. Now, if q is way bigger than n, then this maybe isn't a very good idea. But if q is as small as n, then we have a linear time sort. But only if q is of roughly the same size as n. If this condition is not true, then we need to resort to a more complicated sort called radix sort. Any questions on that? Yeah. Did I skip an item? Okay. Uh-huh. Well, I just write a loop that walks through the buckets one by one, and I always maintain the tail of the last non-empty queue, or the last item in the list so far. And if I hit an empty bucket, I just don't do anything. I skip over that bucket and I go on to the next bucket. And when I hit a bucket that's not empty, I take that queue and I concatenate it to the end of the queue so far. Well, no, because I still have to check each bucket to see if it's empty. So even if all the buckets were empty, it would take queue time just to check that that's the case. So one of the nice things about bucket sort is that it's stable. What does it mean for a sort to be stable? It means that items with equal keys come out in the same order they went in. Now, of the sorts that we've looked at so far, a lot of them are stable, at least if you implement them right. It really does depend a lot on the details of how you implement them, but insertion, selection, and merge sort can all be made stable pretty easily. Now, the linked list version of quicksort can be stable. But the array-based version of quicksort that we've seen is decidedly not stable because of the way it does the swapping of items across the middle of the array. And heap sort is never stable. It just scrambles up those items. Now, that's not entirely true. It's actually possible to make heap sort stable by adding something called a secondary key to all of your items, which I might talk about later in the semester. So again, as I said, bucket sort is only appropriate when Q is distributed in a small range. And if Q is not, we're going to need to solve that. We're going to do that with a more sophisticated sort called radix sort that I'll teach next lecture. But one thing about radix sort is that it uses bucket sort as a subroutine. And when we use bucket sort as a subroutine, the stability of bucket sort is very critical to the success of radix sort. So you'll want to keep that firmly in mind for the next lecture. See you all on question, yeah. Sorry, do you mean the quicksort? Well, the one you had in your homework is a linked list-based version. That one is easy to make stable, but whether or not you actually made it stable in your implementation is up to you. That depends on how you did it. The array-based version I taught in class really scrambles up the keys in a way that doesn't keep them stable.